Now we are going to study about Kepler's second law. Kepler's second law states that the planets, they have dA upon dt is equal to constant. Okay. In one line, if I have to say, this is Kepler's second law. So now Kepler's first law says that the planets, they move in orbits which are elliptical, and at one point you'll have Sun, and at the other any planet. Let us say if we're talking about Earth, although it is valid for all the planets, and so here you have Sun. And so what dA upon dt means is, now because Earth is moving with some velocity v at this point, and let us say that it's after some time it reaches here and it is moving with some velocity v. Now this area from the center of focal point to the Earth, this area, let us say that if this area is traveled dA, is traveled in time dt, then when it reaches here, it will have certain velocity, and let us say it has certain velocity when it reaches here. And this area, if it is also dA, then the time will be also dt, because dA upon dt is constant. Now it means that here Earth has to travel a smaller distance, or any planet has to travel a smaller distance in this amount of time, and here you have to travel a larger distance in this amount of time. It means that Earth will move slowly at this point and it will move fast at this point. It means that the velocity, suppose that if it is v1 at this point and it is v2 in this side, then the velocity v2 should be greater than the velocity v1. Only then can we have dA upon dt equal to constant. Now it means that when Earth is traveling around Sun, it will travel slower when it is far away, and it will travel faster when it is near the Earth. So we can also prove this, that how it is constant. Now let us say that it is traveling with velocity v. Let's talk about any point. Let's draw it again maybe. Let's say that the Earth is moving at this particular point it is moving with velocity v, and it travels from this point to this point, and let us say that this vector is r vector, and this vector from here to here is dr vector. The distance between these 2 points is dr vector, and it is traveling with velocity v, or v vector, and the time it takes to reach from here to this point is dt. So we know velocity, we know displacement, we know time. So velocity vector will be displacement vector upon time. So displacement vector will be velocity vector into time. So, and this area, let us say, is dA. So now, because it is a rotational motion, when this planet is moving from one point to the other, it is changing some angle here. So because it is moving by some angle, so we say that it is rotating. And because it is rotating, we know that in a rotating object, when we don't have any external force here, external force is equal to 0. And if the external force is equal to 0, then the angular momentum will stay constant. Okay, and if angular momentum is constant, first of all, what is angular momentum? Angular momentum is given by r vector cross p vector, and p vector is just simply linear momentum. So we can also write it as r vector cross mv vector, just mass of earth and the velocity with which it is moving. So if I have to find out this area will be, because when we have two vectors, suppose if you have one vector in this direction and let us say that this is r vector, then it makes sense actually, not this one. Let's say this is r vector. So if you have a vector and if you have another vector, let us say it is dr vector, it is r vector, and this is the area we are talking about at the present moment. Then if we just complete this parallelogram, then if this is dA, then this will also be dA. So if we have any vector, let us say a vector, and then you have b vector, and you have to find out this area. This total, if this is dA, this is dA, then twice of dA will be a vector cross b vector magnitude. This is from the vector product of vectors, where this is a rule of parallelogram in vectors, where it says that if you make a parallelogram with two vectors, then their cross product will give you the area in that parallelogram. Okay, so in a similar manner, we can say that 2dA in this case will be r vector cross dr vector. So it means that dA vector will be equal to r vector cross dr vector upon 2. And from here we can say that dr vector is equal to v vector dt. So, and L vector is equal to r vector cross mv vector. Okay, so let us make some, let's put the value of a v vector from here. So L vector will be r vector cross m, and v vector will be d r vector upon dt. Okay, so it means that what we get from this equation is that L vector will be equal to m r vector cross dr vector upon dt. So if I take a magnitude of all of this, then r vector cross dr vector magnitude will be equal to L vector dt upon m. So just put the value here, and it will be dA vector will be equal to L vector dt upon 2m. And therefore dA vector upon dt will be equal to L vector, or let's say we are talking about the magnitudes, then it will be L vector upon 2m. So as you've already said that it is a rotating object, if force is 0, L will be constant, so it will be a constant. And mass of the planet is also constant, so it will also be constant. So it means that this entire quantity will be a constant. Thus we prove the statement we made right at the beginning, that dA upon dt is equal to a constant in planetary motion when the planets are traveling in an ellipse. But what we have to remember from here, that this m is actually mass of the rotating object or rotating planet, whatever it might be. In this case it is Earth, but if some other planet, if Moon is rotating around Earth, then this will be the mass of Moon. If Earth is rotating around Sun, then this will be the mass of Earth, and so on.